All right, so let's move on now to problem number 6 here, which is to find the points of inflection, and also talk about if there's any type of concavity in the house. All right, so points of inflection have to do with the second derivative test, right? So the way that we're going to find our points of inflection is we take the first derivative and then find the second derivative and then find those critical points right there. So that means we're going to set the second derivative equal to 0. And then once we find those values, we have to make sure, though, that the numbers that are to the left of the number and to the right, one's positive, one's negative, because anytime that we have a point of inflection, it always does something like this, where like it's concave down and then it is concave up, or if it's going concave, down here and then it's going to go up right here. So down and then up. It has to switch concavity. So if this is our number that we get right here for our double prime, we set the test the number to the left and to the right, just to make sure, because not all the critical numbers at our second derivative are always going to be concavity, or I'm sorry, are always going to be points of inflection. Okay, so we always got to test it though. All right. So let's go ahead and find the derivative here, and this one is not the nicest guy here, but well, we'll try to be nice back, even though he's not very nice to us. Let's find the prime. So f prime of this guy right here. So we're going to do the product rule. So the prime of x is just 1 times this guy plus x, and I keep marking this up here, and then we get x times the derivative of this guy. Well, this is the same thing as saying x plus 7 to the 1/2, right? So if I'm going to take the derivative, I'm going to go ahead and bring down the 1/2. Okay, so I'm going to multiply that by 1/2 times what's in the middle. I subtract this by 1, so I get negative 1/2. And then if I do the chain rule, the derivative of x plus 7 is just 1, so I don't have to do anything right there. All right, let's go ahead and clean this up now a bit. And I'm going to just go ahead and throw, let's see, maybe I could throw this guy down in the denominator. And let's see here. So I'll go ahead and say x plus 7 to the power of 1/2 plus, I'll put the x on top, put this 2 in the denominator, and then I'm going to throw this whole thing back downstairs. So x plus 7 to the 1/2. Okay. Let's see. What shall we do next? Maybe we can go ahead and see if we can clean this up a little bit more. So what should we do here? Maybe get a common denominator. And I'll just change my color pens here. So maybe on this side now, I'm going to go ahead and multiply this by 2 times x plus 7 to the 1/2. And then multiply this right here, 2 times x plus 7 to the 1/2. Okay, so that means now we'll have a common denominator, and this right here is just going to be x plus 7, right? Because x to the a times x to the b is just x to the a plus b. So 1/2 plus 1/2 is just going to be 1. So up on top we just have 2 times x plus 7. Okay, that's all we're going to get right here. So this whole thing just became 2 times x plus 7. And then we have a plus x all over our common denominator of 2 times x plus 7 to the 1/2. And we can clean this up a tad bit still by multiplying by 2 and blah, blah. So maybe we'll do that. 2x plus 14 plus x all over our denominator. So last but not least, so f prime then is going to be a 3x plus 14 all over 2 x plus 7 to the 1/2. Okay, cool beans right there. All right, so we found the first derivative. We're halfway with finding our primes. So now we want to go ahead and find the second derivative. And I'm just going to go ahead and just write it out. You can work that out yourself here. So my second derivative is just going to be a 3x plus 28 all over 4 times x plus 7 to the 3 halves. Okay, and you could go ahead and just find this derivative by just using the quotient property, and you can get that right there. All right, so now that we have that, okay, the way that we find our point of inflection is we set this whole thing equal to 0. Well, when we have denominator, we just ignore the denominator, and we just set the numerator equal then to 0. So 0 equals 3x plus 28. So I move the 28 over here, and I divide by 3. Okay, so that means we're going to get negative 28 thirds. Okay, so now, so what we want to do is that we want to check. Well, actually, let's do this first. Okay, the point negative 28 thirds. Okay, let's just simplify that right there so that we have a better idea of what's going on there. 3 goes into what? 28. See, 7, 21, 8, 24. So that means negative 8 times. Oh no, hold on. Let me erase that real quick here. My pen at. Okay, so 3 goes into 28 9 times, which is 9 3 is going to give us 27 with the remainder of 1, right? Okay, so negative 28 thirds is negative 9 1/3. Now, if we go back to our problem right now, let's just look at our original problem right now. X times x plus 7. Check this out. What values cannot go in the radical in order to get a real value? Well, negative, right? So every x value must be either negative 7 or bigger. Okay, x must be bigger than or equal to negative 7. Okay, so x could be negative 7, but that means it could be negative 6, negative 5, negative 4, because if we make it negative 8, then now we're going to have a value that's not real. Okay, so if we look at the value that we just got right now, negative 9 1/3. Okay, that tells me, because even if you plug this in right now, it's not even on the graph. That's a value that's not real. So I automatically know when it says find the points of inflection, there are no points of inflections. There's no point of inflection. Because, I mean, if you plug the value in, you won't even get a real value. So we kind of just did the first part right now, kind of intuitively by just looking at the point, like, wait a minute, this is even outside of the range or the domain of what is possible here. Okay. Now the way that, like we learn though, is we take this point, okay, negative 28 thirds, right? And then we cut it right here, and then we say, okay, what's happening to the left of it, and then what's happening then to the right. And I'm going to do it that way right now, but we already know what we're going to get. Okay. So I need to find any value that's to the left of negative 9 1/3. So let's just do negative 10. So let's find f of double prime of negative 10. And all we're interested in is the sign. Well, look, if I plug in negative 10, and look what we get. Does not exist. Okay, so you would get that right now and say, oh, well, I'm done. But let's just see what happens then to the right. Maybe we'll just do 0 then. So f double prime of 0. If I plug in a 0 right here, 0's everywhere. Well, that means I'm going to get a positive number. So at least this information is going to be helpful, because we come up here and discuss the concavity of it. So it never does a concave down, but this right here, from negative 28 thirds to infinity, it's going to concave up. Okay, and that's just because we get a positive number there. And if we just graph that real quick, I should have maybe graphed it before, but I'm just going to do it real quick right now, just to kind of make sure that we were on the right track there. And what is it? X times x plus 7. Go ahead and graph that guy right there. And let me just get a better zooming window. Good. And this is what the graph looks like right here. It looks something like this. And it does this thing. Kind of like a little check mark there, right? And that's why it does concave up the entire time. It never concaves down. And there is no point of inflection because it never does a concave up and then a concave down anywhere. Okay? Let's go into problem number 7 now. And we want to locate the absolute extrema, meaning what's the maximum and the minimum point of this graph right here on this closed interval. So let's find the prime. Negative 4x plus 12. Can we find the zeros of that? So 0 equals negative 4x plus 12. Subtract 12. And divide by negative 4. And we get 3 right there. So I want to check now. 3, 6, and negative 6. So what's f of 3? What's f of negative 6? And what's f of 6? And when we test all those points, the highest wins the maximum, and the lowest wins the minimum. So f of 3 is 22. So that means you're just evaluating, plugging it into here. F of negative 6 is negative 140. And f of 6 is 4. So my winners go like this. So this right here is going to be our max. And this guy right here will be my minimum. And there's that guy right there. Problem number 8 now, graph f. The graph of f is shown. Find or sketch the derivative of f. Okay, so, again, this is just a sketch right here. And so let's see here. If you kind of look at this point down here, we have a very steep derivative. It's very negative, so I know it's going to start way down here. But maybe the approach that I want to take is this. You see how our function has a 0 and a 0 of 2. So really, if I put that as linear factors, this quadratic f of x has a 0 at 0 and a 0 at positive 2. Meaning if I multiply this out, or if I set this equal to 0, I get 0. If I set this equal to 0, then I get 2. So basically all I'm doing is I'm working backwards, and I'm creating a function that has a 0 at 0 and a 0 at 2. So really our function, we're looking at x squared minus 2x. So if I find the derivative of that, I just get 2x. And so basically you would just graph, excuse me, as you graph, we're going to graph f prime of 2x. Well, that means there's just a line 2x right there. So that means start at, I'm sorry, and then minus 2 right here. So that means I start at negative 2, and I go up 2 over 1. And I just go ahead and connect those guys, and that's going to give us a point right there. So it'll look something like that there. So that's what your derivative should look like. And this is more of an algebraic way. But if you didn't want to do that, like you could have just said, okay, that derivative, oops, I'll get rid of that right there. Okay, so like that derivative right there is very negative. So I go right here, and then this derivative right here isn't so negative. This derivative right here is very, very small, so that's why it keeps getting closer to the x-axis. So you could have done it that fashion as well. Okay.